Jai Hind everyone. This is Dr. Naresh Kumar from Akgec Engineering College, Ghaziabad. Welcome to the class of Optical Communication. So under Unit 2, in this video lecture, basically we will discuss the dispersion-modified single mode fiber and also the non-linear effects. So the main contents of the lecture will be dispersion-modified single mode fiber. Basically we know that the dispersion characteristics or dispersion response of a single mode fiber can be modified by tailoring the parameters. So after modification, three types of single mode fiber can be obtained, that is dispersion shifted fiber, dispersion flattened fiber and non-zero dispersion shifted fibers. And along with this topic we will also cover the non-linear effect. The non-linear effect are mainly here are Kerr effect, and further that has types such as SPM, XPM and 4-wave mixing, that is FWM. So we will cover these two topics in detail. So the first topic for today's lecture is dispersion modified single mode fiber. Basically we know that the dispersion characteristics or dispersion graph, or we can also say that the dispersion response for a single mode fiber can be modified or can be changed. For example, in the single mode fiber we get a zero dispersion point at a wavelength around 1.3 micrometer. So this point of zero dispersion wavelength can be shifted from 1.3 to 1.5, let's say. So the dispersion characteristics or dispersion response of single mode fiber can be obtained, and after changing the characteristics we get the modified fiber, and there are different types for this dispersion modified fiber. So let's see the total dispersion for a single mode fiber is basically mainly given by the combination of material dispersion and contribution from the waveguide dispersion. We know that in the single mode fiber the total dispersion is mainly given by the material dispersion, then we have waveguide dispersion, and sometimes we also have the profile dispersion, DP. Out of these three, this profile dispersion is generally negligible, and generally this material dispersion is dominating. Okay, so the combined response of single mode fiber is given by the combination of material dispersion and waveguide dispersion. So the material dispersion is given by this formula, and whereas the waveguide dispersion is given by this formula. So from this we can get an interesting fact here, is that this total dispersion depends upon material dispersion and this waveguide dispersion, and we clearly see that the sign for this waveguide dispersion is with negative sign. That is, if we change the parameters available in these two formulas, then accordingly the value of dispersion will also change. So the dispersion response or characteristics will be modified. So the dispersion characteristics of single mode fiber can be modified by tailoring the specific fiber parameters. These parameters which can be modified or changed are, for example, here we have the operating wavelength lambda. Lambda can be modified. Here we have the refractive index of the core N1. So lambda is there, N1 is there. Then we have cutoff wavelength lambda C, it is there. Then we have V number, normalized frequency V number is there. Then we have normalized propagation constant B, and we also know that the formula for V number is V equal to 2 pi by lambda a n1 2 delta power 1 by 2, that is numerical aperture. So we can also modify the value of V by modifying the parameters such as, that is radius of the fiber, numerical aperture, or we can also say that delta, relative refractive index difference. So these are the parameters. By modifying these parameters, we can modify the response, dispersion response for the single mode fiber. That is, if we change the values of these parameters, then the total dispersion corresponding to the single mode fiber will be modified, or dispersion characteristics will be modified, and the fiber obtained in this case will be known as the dispersion modified single mode fiber. So let's see with the help of characteristics how we can do that. So this is the dispersion response for a single mode fiber. Let's say in this direction we have the wavelength, and here we have the dispersion. Okay. So the dispersion for the single mode fiber is given by like this. This is the dispersion characteristics for the single mode fiber. So these are the characteristics for a standard single mode fiber. Standard single mode fiber. Okay. So this zero dispersion wavelength is at around 1.31 micrometer. Now in the dispersion modified fiber, this dispersion characteristics can be shifted from one point to another point. Let's say this dispersion characteristics may be shifted to another point like this. So at this point it is 1.55 micrometer. So the zero dispersion point has been shifted from this 1.3 to 1.55 micrometer, because we know that at 1.55 micrometer we have attenuation also as minimum or 0. So at this point, shifting this dispersion characteristics from 1.3 to 1.5, we get both advantages, that is dispersion is also minimum and attenuation or losses are also minimum. So this is the case of fiber known as the dispersion shifted fiber. Okay, so this type of fiber is known as the dispersion shifted single mode fiber, or this is DSF. Okay, another type of dispersion modified single mode fiber is known as the dispersion flattened fiber. Dispersion flattened fiber, that is DFF. So as clear from the name, for this type of fiber we will get a flat dispersion response in a particular given range of wavelengths. For example, this dispersion characteristics can be shifted like this. So between 1.3 to 1.6, let's say this is 1.6 micrometer and this is 1.3 micrometer. So here what we are getting is, we are getting a flat dispersion response in a given range of wavelength 1.3 to 1.6 micrometer. So here this type of fiber or dispersion modified single mode fiber is known as the dispersion flattened fiber. Another type of fiber that we can get after modifying the dispersion characteristics of single mode fiber can be a positive dispersion fiber or a negative dispersion fiber. For example, this standard single mode characteristics can be shifted to a point below this 0. So this can be shifted at this point. So we can get the characteristics or response like this. So here we have the positive values for the dispersion, here we have the negative value. So where this dispersion characteristics are shifted below this 0 level, and this type of dispersion modified fiber is known as, for example, zero dispersion fiber, or we can also say that as this value negative. So we can also say that this is negative dispersion fiber, NDF. Okay. So in conclusion, we can see that the dispersion characteristics of a standard single mode fiber can be shifted from one point to another point. We can get a flat dispersion response in a given range of wavelengths, or we can also shift this dispersion characteristics to a positive value or a negative value. So accordingly we can get different type of dispersion modified fibers, such as first type is dispersion shifted fiber, another type is, for example, dispersion flattened fiber, another type is, for example, is negative dispersion fiber, so it is NDF, negative NDF, or negative, or that can be positive, or we can say that non-zero. We can also say that this is non-zero. Okay. So these are the characteristics of a standard single mode fiber. These are the total dispersion characteristics for a various type of single mode fiber. As discussed previously, these are the characteristics corresponding to a standard single mode fiber, where we have a zero dispersion wavelength around 1.3 micrometer. Then two type of fibers are shown here. Then this zero dispersion point is shifted from 1.3 to around 1.55 micrometer. So this type of fiber is known as the dispersion shifted fiber, or already known as dispersion shifted fiber, DSF. Then we have a flat dispersion response in a given range of wavelengths, let's say 1.3 to 1.6. So this is the 1.6 point and this is the 1.3 micrometer. So in this type of fiber we get a flat dispersion response in a given range of wavelength. So this type of fiber is known as the dispersion flattened fiber, DFF. Okay. So these are the cases that we have discussed. Now the point is how we can obtain these different type of fibers, dispersion shifted fibers. Basically, as discussed, the dispersion shifted fibers can be obtained by changing the parameters, or tailoring of parameters. The parameters which can be modified, that we have discussed in previous slides. So basically the structure of fiber is modified. Mainly the fiber structure is modified. Example of this modification can be, for example, first type that we are discussing is dispersion shifted fiber. In the dispersion shifted fiber, the zero dispersion wavelength is shifted from one point to another point. Let's say from 1.3 to 1.55 micrometer. So how we can obtain this? This can be obtained by simply doing two things: by reducing diameter, the diameter of the fiber, that is changing the A. Another is by increasing index difference, or relative index difference. or in terms of delta profile, index profile. So simply by changing the diameter and changing the index profile parameter, we can get this type of fiber, dispersion shifted fiber. Example of this is shown here. This is the modification example in the structure for the case of dispersion shifted fiber. Okay, where this solid line is for, this is the dispersion shifted fiber, and whereas this non shifted fiber are those dash line. This is the standard fiber. So what we have done is we have reduced this. This was the original diameter. Now this is the reduced diameter. Now we have also changed this delta n, that is index profile. So this is also changed. So by changing this index profile and by varying the diameter, we will get the dispersion shifted fiber, that is DSF. In the similar way, by changing or modifying the structure, we can get the additional type of dispersion modified fibers. That characteristic here. These are another examples of the index profile. We can get different type of fibers for modifying the index profile. So these are the profiles for the graded index fiber. If we have to obtain the dispersion shifted fiber, and the standard single mode fiber is basically a graded index fiber. So these three are the examples for the index profile that can be used with the graded index fiber for obtaining the dispersion shifted fiber. These are some more examples. These are the profile index designs that can be used for obtaining dispersion shifted fibers. Another is dispersion flattened fiber. As discussed, here we get a flat dispersion response in a given range of wavelengths. The dispersion flattened fiber can be obtained, for example, by utilizing the multiple clad structure. Multiple clad structures are used for obtaining or achieving the dispersion flattened fibers. For example, these three structures are shown here. One is it is the double clad structure. This is the three clad structure, and this is the four clad structure. Four clad structure, or also known as a quad, and this is the two clad. Okay, so this one is the first cladding, this is the second cladding. This one is the first cladding, second cladding, and this is the third clad structure. And here we have the first clad, second clad, third clad, and fourth clad. So by utilizing the multiple cladding based optical fiber structure, we can achieve the dispersion flattened fibers. However, one limitation with these multiple clad structure is that careful designing is very important. Careful design and separation or fabrication is important. If the design is not careful, then sensitivity towards the bending losses and other type of irregularities or separation problem can be increased. So we have to take care while designing the multiple clad structures. Next is non-zero dispersion shifted fibers. That is, we can get the dispersion response characteristics either above zero dispersion level or below zero dispersion level. And one example for this is, for example, NDF, that is negative dispersion fiber. As discussed in the response, like this, these are, here we have the dispersion, that is positive, negative. Here we have the wavelength. This is the standard response, standard characteristics. Now for the negative dispersion fiber, this characteristic is shifted below the 0 point. So if this type of response is there for the standard single mode fiber, then this will be known as the negative dispersion fiber. So this is the example of negative dispersion fiber. Then how we can achieve this negative dispersion fiber? Like previously discussed, this can be again achieved by modifying the parameters or simply by changing the index profile. Index profile design can be modified for achieving different type of fibers. One example is here shown here, as shown discussed in the previous slide. So these are the characteristics corresponding to the negative dispersion fiber. These are the two examples of typical refractive index profiles that can be used for achieving the non-zero dispersion shifted fiber. Non-zero dispersion, A part is there, and this type of index profile can be used for achieving the negative dispersion fiber. So negative dispersion fibers can also be obtained using this type of index profile design. Next is non-linear effect. Another topic for today's lecture is non-linear effects. Basically, non-linear effects are undesired and these usually occur at higher optical power levels. And moreover, these non-linear effects can result into change of frequency or phase. These can cause change in frequency or phase. If there is any change in the frequency, then this type of phenomena that we are discussing is known as the scattering. This happens in the scattering case, and this type of scattering is known as the non-linear scattering, where the power is transferred in a disproportionate manner and there is change in the frequency of the signal after scattering. And whereas change in the phase, this type of phenomena that we are discussing is known as the Kerr effect. Okay, basically whenever the light interacts with the material of the fiber, there is some kind of phenomena, either there is absorption, then there is scattering, and if the intensity of light is too much high, then the refractive index of the fiber material can also be modified. So this type of interaction can result into non-linear phenomena. Example of these non-linear phenomena are non-linear scattering and Kerr effect. These are the basic various type of non-linear effects that are occurring into the fiber. Basically, these non-linear effects are divided into two categories. First is known as the Kerr effects. Second is known as the scattering effects, or we can say that this is the non-linear scattering. That is a separate topic that we discuss. The non-linear scattering can be SRS and SBS. That we have already studied, whereas this SRS and SBS is mainly at lower threshold, and this SBS is mainly a backward process. That is, power transfer usually occurs in the backward direction, whereas this SRS occurs at comparatively higher threshold and this is mainly both backward direction and forward direction. That is, SRS can occur both in forward direction as well as in the backward direction. There are other differences as well as, in this case, a acoustic phonon is produced, whereas in the case of this SRS we get a optical phonon as an additional particle. And all the characteristics of nonlinear scattering are followed here, like power is transferred in a disproportionate manner, and after scattering there is a change in the frequency of the signal. So now what is Kerr effect? Kerr effect is basically a nonlinear effect where the refractive index of the material becomes intensity dependent. So whenever we have high intensity signal, the refractive index gets modified or changed, and changing in this refractive index is a kind of waveguide perturbation. And this kind of waveguide perturbation can result into change in phase. This change in phase is termed as the Kerr effect, which appears as a kind of phase modulation. Basically, in the case of Kerr effect, we have the refractive index of the fiber becomes intensity dependent, and this refractive index, changing refractive index can cause the change in the phase of the signal, and this is termed as the Kerr effect. This Kerr effect can be of three types: SPM, XPM and FWM. Whereas in the case of SPM, that is self phase modulation, what we have is the signal which is responsible for change in the refractive index of the material, then the corresponding phase of the same signal gets changed. That is, the signal which is responsible for the change in the refractive index, that signal phase is changed. So that's why it is known as self. Another is cross phase modulation. Here one signal cross, this is the cross XPM. Here the one signal which is responsible for change in the refractive index cause the change in the phase of the another signal or adjacent signal. That's why this is known as the cross phase modulation. Another is four wave mixing. This is basically used for generating signals in the case of multiplexing, generating different frequency signals in the case of multiplexing. For example, WDM. Here what we have three different signals combined together to generate a fourth frequency signal. So we have a fourth frequency signal, that is by the combination of three different signals, okay, which can be same or different. So this type of phenomena is known as the four wave mixing. So that's all for this lecture. Thank you everyone. Jai Hind.